The vast silence of the cosmos holds a secret measured in darkness and kinetic energy, a secret now unfolding behind the blinding light of our own sun. This is the story of 3I, Atlas, the third confirmed visitor from another star system, and its terrifying passage through our inner solar realm. We begin in a shadow. The date is late, October 2025, and an object estimated to be 5.6 kilometers across a mass of 33 billion tons is utterly invisible to human eyes and instruments. It is lost to us not because it is too far, but because it is too perfectly hidden by the fierce gravity and light of the star we call Sol. On October 21-3, I-Atlas achieved what astronomers call solar conjunction. It slipped precisely behind the sun from our earthly vantage point, a maneuver that guarantees its total observational blackout. For weeks, we will see nothing of this interstellar traveler. Yet the greatest drama of its journey is unfolding right now, in that cosmic blind spot. Even as we listen to the calming rhythm of the narrative, the object is accelerating toward a point of no return, a crucial junction in space-time that the laws of physics define as the moment of maximum power. On October 29 or 33, I-Atlas will reach its perihelion, its closest approach to the Sun, at a distance of 1.36 astronomical units, or 203 million kilometers. This distance places it just inside the approach to the Sun, orbit of Mars. And in astronautics, the moment of closest approach to a massive body is the optimal time for a deep space maneuver. This is the gravitational slingshot amplified by human design known as the Oberth Effect. The principle dictates that if you apply a burst of thrust, say from an engine or a massive plume of gas at the point of highest orbital velocity, you gain the maximum possible increase in speed and kinetic energy for the smallest expenditure of fuel, 3I. Atlas is already moving at an astounding 210,000 kilometers per hour, the highest speed ever recorded for a solar system visitor. The coincidence is chilling the point of maximum dynamic leverage. The perihelion is happening. During the exact period, the object is hidden from our view. A time of guaranteed obscurity is the time of optimal high-energy action. Harvard astrophysicist Professor Avi Loeb, director of the Galileo Project and former chair of astronomy at Harvard University, has framed this temporal alignment not as a subject of physics, but as a philosophical challenge. The question he poses to the universe echoes in every empty telescope lens pointed toward the Sun, direct source. Attribution. Was this a mere coincidence, or a result of orbital design and basic astronautics? He suggests that if 3I Atlas were in fact a massive mothership, then this maneuver could apply not to the core object itself, but to smaller probes or craft released at perihelion and directed toward the planets of our system. This speculation that an optimal time for technological action is being leveraged during a total blackout elevates 3I Atlas from a natural phenomenon, a cosmic question mark. But even without the element of conscious design, the object is already an extreme outlier defined by its terrifying natural power. For months, scientists had been tracking its immense activity and realized early on that this was no ordinary comet. Its brightening rate, as it approached the Sun, was measured as exceptionally steep, following a power law proportional to R-H circumflex, -3. 8, where R represents the heliocentric distance. To put that in perspective, the previous interstellar comet 2I, Borisov, had a relatively shallow index proportional to R-H circumflex -1.9. 3. I, Atlas, is a volatile beast driven by an engine of deep space ice. Observations from instruments like the Nordic Optical Telescope confirmed a critical fact. The motor driving this extraordinary activity is not water ice, the traditional cometary fuel, but frozen carbon dioxide. Specifically, the sublimation of CO-2 ice is the primary driver. Carbon dioxide sublimates at much colder temperatures, meaning 3. I, Atlas, began its dramatic outgassing far earlier and far more violently than a standard comet. This CO2 activity is what fuels the bizarre visual evidence we are seeing in the composite imagery, a feature known as the anti-tail. Instead of the dust streaming safely behind the frozen seed nucleus away from the sun, new images show the object spitting out an enormous jet of gas and dust straight toward the sun. This fan-shaped plume, described by scientists as a giant jet blasting toward the sun, is the consequence of the most intense non-gravitational forces ever recorded for a visitor in our system. At its peak activity 3, I-Atlas was shedding material at a rate of 180 kilograms per second at 2 astronomical units, more than double the rate of 2 I-Borisov at the same distance. This extreme, unpredictable ejection of gas and dust has done more than excite scientists like Professor Darryl Seligman from the Physics and Astronomy Department at Michigan State University, who calls it direct source attribution. Hugely exciting DIRST discovery. It has crossed the line into a matter of planetary defense 3. I-Atlas has become the first ever interstellar object officially added to the monitoring list of the International Asteroid Warning Network, or IAWN. IAWN, a United Nations endorsed group focused on Earth protection against near-Earth objects, has never before included a visitor from another star. Their officials have made a sober admission that the sheer volatility and intense non-gravitational forces of the CO2 jet are causing direct source attribution unique challenges for predicting its trajectory. They have to model not just gravity, but the chaotic force of an alien engine that is doubling the output of its predecessor. The institutional response is an escalation, a global stress test for our celestial defense systems. IAWN has announced a special exercise, the Comet Astrometry Campaign, scheduled to run from November 27-20-25 to the 27th of January 2026. The sole purpose of this 2-month-long campaign is to focus every available telescope and tracking system across the globe on 3 I-Atlas. This is a drill designed to refine techniques for precisely locating it in the sky and understanding its complex motion. The timing of this campaign is not accidental. It begins precisely when 3 I-Atlas is expected to re-emerge from behind the sun in the sestit, pre-sunrise sky. Around early December, the tension is now locked. In a planetary defense network is preparing to scour the sky for a 5.6-kilometer object that just spent weeks hidden at the optimal point for either a catastrophic physical transformation or a mysterious technological actio. The next step in this cosmic detective story is entirely dependent on what we find when the veil of the sun is finally lifted. Will the trajectory be clean and predictable, merely a powerful natural phenomenon, or will the trajectory, non-gravitational forces, have changed its course in ways we cannot yet foresee? And, more chillingly, will we find the small shadow of a companion, a subtle object that confirms the speculation of a purposeful maneuver? Thank you for being with us. please subscribe and leave a like. To understand why this moment carries such weight, we must journey backward through the brief but revolutionary history of interstellar visitors. The story begins on the 19th of October 2017, when astronomers using the Penn telescope in Hawaii detected an object moving through our solar system at an impossible angle. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. It came from somewhere else, and it would leave again. This was one Oumuamua, the first confirmed interstellar object, a name meaning scout or messenger. In Hawaiian, Oumuamua was strange. From the moment of discovery, it was tumbling end over end with an elongated, cigar-like or pancake-like shape. And it showed no cometary activity, no tail, no outgassing. Yet as it whipped around the sun and headed back into deep space, something unexplained happened. It accelerated slightly faster than gravity alone could account for. This tiny, non-gravitational acceleration sparked fierce debates. Was it outgassing too faint to detect? Was it radiation pressure on an unusually reflective surface? Or, as some, including Avi Loeb, suggest, could it be a technological artifact, a light sail, pushed by the pressure of starlight? We never got a close look. Oumuamua was discovered only after it had already passed perihelion, and by the time we understood what we were seeing, it was already racing away from us, fading into the cosmic dark. The second visitor arrived on the 30th of August 2019, when amateur astronomer Gennady Borisov, using a telescope he built himself, spotted a fuzzy comet-like object approaching the Sun, designated 2I Borisov. This was a far more cooperative subject. It behaved like a classic comet, complete with a prominent tail driven by the sublimation of water, ice, and carbon monoxide. Scientists had months to study it. With every available instrument, from ground-based telescopes to the Hubble Space Telescope, Borisov was recognizable. A traveler, yes, but one that fit comfortably within our understanding of cometary science. Its composition, its activity, its structure, all resembled comets born in our own solar system. It was exotic in origin, but familiar in nature. It followed the rules. And now we have 3I Atlas, a visitor that shatters those rules. The object was discovered earlier in its approach, giving astronomers precious time to observe its evolution as it dove toward the inner solar system. What they witnessed was acceleration of activity on a scale never seen in an interstellar visitor. The brightening curve, that steep RH circumflex, -3.8. Relationship told them that something was driving this comet with far more fury than water ice alone could explain. The breakthrough came when spectroscopic observations revealed the smoking gun S. Strong emission lines of CO2 carbon dioxide ice is the fuel of the outer solar system. It freezes at temperatures far below the frost line of water. When a comet rich in CO2 begins to warm, even at distances of several astronomical units from the sun, the ice begins to sublimate, transitioning directly from solid to gas without passing through a liquid phase. This phase transition is explosive. The gas expands violently, carrying with it dust particles that were frozen into the ice matrix, creating the brilliant clouds and tails we associate with comets. For 3I Atlas, this process began early and intensified rapidly. At 2 astronomical units, roughly twice the Earth-Sun, to distance, the object was already outgassing at 180 kilograms per second. By comparison, 2I Borisov, at the same distance, was releasing only about 80 kilograms per second. This is more than twice the activity, and it created a problem. Comets are not inert objects flying on purely gravitational trajectories. Every kilogram of gas they expel creates a tiny rocket thrust, pushing the nucleus in the opposite direction. For a comet like 3, I Atlas, with such extreme and asymmetric outgassing, these non-gravitational forces become dominant. They can alter the trajectory by thousands of kilometers over the course of months, making precise predictions of the comet's future path extraordinarily difficult. This is the core problem facing IAWN and the planetary defense community. When you are tasked with protecting Earth from celestial threats, you need to know where an object will be weeks or months in advance with pinpoint accuracy for asteroids. This is relatively straightforward. They follow clean Keplerian orbits dictated purely by gravity. But for active comets, especially one as violent as 3, I, Atlas, the equations become a nightmare. You must model not just the sun's gravity, but the chaotic reactive forces of sublimating ice, jetting in unpredictable directions, the CO2 engine of 3. I Atlas is not a steady, reliable thruster. It is a storm. The newly released imagery adds another layer to the mystery. The anti-tail, that sharp fan-shaped jet of material pointing toward the sun rather than away from it, is a rare phenomenon in cometary science. Most comets develop two tails, a dust tail that follows the orbital path, curving gently behind the nucleus, and an ion tail, a straight beam of charged particles blown directly away from the sun by the solar wind. But under certain geometric conditions, when Earth passes through or near the plane of a comet's orbit, we can see dust particles that were ejected earlier and are now spread along the orbital path, appearing to point forward toward the sun. For 3, I Atlas. This anti-tail feature is not just a matter of perspective. It is evidence of the intense asymmetric jetting driven by COC to sublimation on the sunward side of the nucleus. The fact that scientists can observe this structure in such detail tells us the object is shedding material at a prodigious rate, creating a dust environment dense enough to scatter sunlight and reveal the geometry of the outburst. Professor Jason Wright, director of the Penn State Extraterrestrial Intelligence Center and professor of astronomy and astrophysics, has emphasized the scientific value of this rare opportunity, direct source attribution. This is only the third interstellar comet we have been able to study, allowing planetary scientists to learn about comets from other solar systems. Each interstellar visitor is a probe sent not by intelligence, but by the chaotic dynamics of stellar evolution and planetary formation. Each one carries in its ice and rock and organic molecules a snapshot of the conditions in another star system billions of years ago. By studying the composition of 3I Atlas, by measuring the ratios of different isotopes of carbon and oxygen and nitrogen, by analyzing the dust grains and the organic chemistry, we are in effect conducting remote sensing of alien worlds we will never visit. We are reading the chemical biography of a star system light years away, written in the language of sublimating ice. Yet the timing, the geometry, the confluence of invisibility and maximum kinetic opportunity continues to haunt the discussion. Avi Loeb's question lingers in the data like a shadow, direct source attribution. Was this a mere coincidence, or a result of orbital design and basic astronautics tuition? Understand why this question is not immediately dismissible as fringe speculation. We must consider the Oberth effect in detail. The principle is named after Hermann Oberth, one of the founding fathers of rocketry and spaceflight, who described the phenomenon in the early 20th century. The mathematics are elegant and unforgiving. When you are moving at high velocity relative to a gravitational body, any change in velocity, any delta V, pli, is amplified in terms of the resulting change in kinetic energy. This is because kinetic energy scales with the square of velocity. If you fire a rocket engine while moving at 10 kilometers per second, you gain far more energy than if you fire the same engine with the same fuel while moving at 1 kilometer per second. For interplanetary or interstellar missions, this means the most efficient place to perform a trajectory correction or a major burn is at Perihelion, point of closest approach, where orbital velocity is at its maximum. For 3I Atlas, traveling at 210,000 kilometers per hour, as it rounds the Sun, any thrust applied during those critical hours near perihelion, whether from a rocket engine or from asymmetric outgassing, will have maximum effect. If the object were to release smaller craft or probes, as Loeb suggests, this would be the moment to do it. The physics would naturally carry those objects into a wide variety of trajectories, with minimal energy expenditure, and the timing of the solar conjunction ensures that this moment of maximum efficiency is also the moment of maximum obscurity. We cannot see it happen. We can only measure aftermath when the object emerges from behind the Sun in December, and we recalculate its trajectory, comparing the predicted path based on gravitational models to the actual observed position. Any deviation, any unexplained acceleration or deceleration will be a clue carved into the fabric of space-time itself. The IAWN Comet Astrometry Campaign is humanity's attempt to read that clue with the highest possible precision. From the 27th of November, 2025 through the 27th of January, 2026, dozens of telescopes across multiple continents will track 3I Atlas, night after night, measuring its position against the fixed background of stars with sub-arcsecond accuracy. Astrometry, the science of precise positional measurement, is one of the oldest branches of astronomy, dating back to the ancient Greeks, who charted the wandering planets against the zodiac. But modern astrometry, aided by charge-coupled device cameras, adaptive optics, and space-based observatories like Gaia, can measure positions to milli-arcsecond precision, revealing motions and accelerations invisible to earlier generations. This campaign is both a scientific necessity and a symbolic moment. It is the first time the global planetary defense network has mobilized around an interstellar object, treating it not as a curiosity, but as a potential threat, or at least as an object whose trajectory must be known with absolute certainty. The fact that 3I Atlas is traveling on a hyperbolic escape trajectory, meaning it will leave the solar system and never return, might seem to reduce the threat level. After all, an object that is leaving cannot impact Earth. But the concern is more subtle. What if the non-gravitational forces are strong enough to bend the trajectory in unexpected ways? What if the CO2 outgassing is asymmetric enough to alter the object's speed or direction in ways that bring it closer to Earth's orbit than currently predicted? What if, and this is the speculative edge, what if there are secondary objects, smaller fragments, or hypothetical probes that could be ejected with different trajectories? These are the questions driving the campaign, and they are questions born from the unique properties of this object, its extreme activity, its unprecedented CO2 engine, and its hidden passage through perihelion. As we wait for the object to reappear, we are left with a peculiar form of suspense. Scientific suspense, rooted not in fiction, but in the hard limits of observation and the cold equations of orbital mechanics, somewhere beyond the glare of the Sun hidden in a corona of light 3. I-Atlas is completing the most critical phase of its journey past our star. In less than a week from now, it will reach Perihelion, and if the forces acting upon it are as powerful as the data suggests it, will emerge in December as a changed object, brighter or dimmer, faster or slower, on a trajectory that either confirms our models or defies them. The next 35 days are a countdown not to disaster, but to revelation, and in the quiet hours of the night. As astronomers prepare their instruments and planetary defense analysts refine their software, the question posed by Avi Loeb hangs in the air unanswered. Was this timing a coincidence or a choice? And if it was a choice, whose choice was it? The universe, we are learning, does not always provide clear answers, but it always provides data, and the data from 3I-Atlas, when it finally emerges from the shadow of the sun, will be the most closely scrutinized measurements in the history of interstellar astronomy. This is where part one of our story pauses on the edge of the unknown, with humanity watching and waiting for the visitor to return to view. The science of INTE, our stellar objects, is the science of the unexpected. Every assumption we held about comets and asteroids, every model built from centuries of observing objects born in our own solar system, must be questioned when we encounter a visitor from beyond. For 3I-Atlas, the unexpected has become the defining characteristic, and as we move deeper into this investigation, we must ask, what makes this object so fundamentally different from everything that came before? Let us begin with the Perihelion, concept of origin. When we observe a comet in our solar system, we know its birthplace with reasonable certainty. Most comets originate in two vast reservoirs of icy bodies, the Kuiper Belt, a disc-shaped region beyond Neptune populated by millions of frozen worlds, and the Oort cloud, a spherical shell of cometary nuclei extending nearly halfway to the nearest star. These are the archives of our solar system, preserving material from the protoplanetary disk that gave birth to the Sun and planets 4.6 billion years ago. Comets from the Oort cloud are nudged into the inner solar system by gravitational perturbations from passing stars or the tidal force of the Milky Way's galactic disk. They fall sunward on long elliptical orbits, taking thousands or millions of years to complete a single circuit. When they approach the sun for the first time, they are called dynamically new comets, and they often display dramatic outbursts as pristine. ICES encounters solar heat for the first time in billions of years, but 3I-Atlas is not bound by our sun's gravity. Its trajectory is hyperbolic, meaning it arrived with excess velocity from interstellar space, and will depart the same way. This object was born around another star in another planetary system under conditions we can only infer from the chemistry it carries. The fact that it is rich in carbon dioxide tells us something profound about its formation environment. CO2 ice is stable only at very cold temperatures, below approximately 80 Kelvin or minus 193 degrees Celsius. For a comet to accumulate significant amounts of CO2 during its formation, it must have formed in the outer regions of its parent star system, far from the warmth of its sun, in a zone where volatiles like carbon dioxide, methane, and nitrogen could freeze solid. This suggests 3I-Atlas originated in a region analogous to our own Kuiper Belt or Oort cloud, but in a system that may have had different chemical abundances, different ratios of carbon to oxygen, or different thermal histories. The isotopic composition of the gases we detect from 3I-Atlas could reveal the temperature and chemical conditions of that alien protoplanetary disk billions of years ago. Spectroscopy, the science of analyzing light to determine composition, is our primary tool for this investigation. When sunlight passes through the gas cloud surrounding 3I, Atlas, the atoms and molecules absorb specific wavelengths of light, creating dark absorption lines in the spectrum, or they re-emit light, characteristic wavelengths, creating bright emission lines. By measuring the exact positions and strengths of these lines, scientists can identify which molecules are present and in what quantities the detection of strong COC, 2 emission flow, M3I. Atlas was a landmark result published in observational reports from facilities like the Nordic Optical Telescope and others. It confirmed that carbon dioxide, not water, is the dominant driver of activity as the comet approached the probeless inner solar system. This is unusual even among interstellar visitors. 2I Borisov showed strong water and carbon monoxide signatures, but CO2 was a secondary component. For 3I Atlas, CO2 is the star of the show, and its sublimation rate creates the massive outgassing that is complicating trajectory predictions. The process of sublimation is governed by thermodynamics and the specific properties of the ice. As 3I Atlas approaches, the sun's solar radiation heats the surface of the nucleus. The temperature rises, and when it crosses the sublimation point for COCO2, the solid ice transitions directly to gas without melting. This gas expands rapidly, escaping from the nucleus at speeds of several hundred meters per second, carrying with it dust particles that were embedded in the ice matrix. The gas and dust form the coma, the cloud. Surrounding the nucleus and the pressure of sunlight, the solar wind pushed this material outward, creating the tail. But the process is not uniform. The nucleus of a comet is not a smooth sphere. It is an irregular rubble pile of ice and rock with cliffs, valleys, and craters. Some regions may be more active than others, depending on the composition, the amount of sunlight they receive, and the thermal properties of the material. If one side of the nucleus is sublimating more vigorously than the other, the escaping gas acts like a rock, at exhaust, pushing the nucleus in the opposite direction. This is the source of non-gravitational forces, and for 3I Atlas, these forces are extreme. The anti-tail feature visible in recent images provides a window into the geometry of this outgassing. The term anti-tail is somewhat misleading. It is not truly a tail pointing toward the sun, but rather a perspective effect. When Earth passes through or near the plane of the comet's orbit, we see dust, particles that were ejected earlier in the orbit and are now spread out along the comet's path. From our viewpoint, these particles can appear to form a spike or jet pointing sunward, especially if the comet has been shedding material asymmetrically. For 3I Atlas, the anti-tail appears as a sharp, fan-shaped structure, indicating that the outgassing is highly directional, likely originating from a specific active region on the sunward-facing side of the nucleus. This kind of jetting is common in comets, but the intensity and the scale of the structure for 3I Atlas is extraordinary, suggesting that a significant fraction of the nucleus surface is actively sublimating. There is a deeper question embedded in this observation, one that touches on the nature of cometary nuclei and their internal structure. Comets are not solid blocks of ice. They are porous aggregates held together by weak gravity and the cohesive strength of ice. If the outgassing is too intense, it can overcome the structural integrity of the nucleus, causing it to fragment or disintegrate entirely. This has been observed in several comets throughout history. One famous example is Comet Shoemaker-Levy 9, which was torn apart by Jupiter's tidal forces in 1992 and subsequently collided with the giant planet in 1994. Another is Comet Linear, which broke apart in 2000 as it approached the Sun, the increasing solar heat and outgassing pressure fracturing the fragile nucleus. Could 3I Atlas suffer a similar fate? The object is estimated to be 6 kilometers in diameter, large enough that its self-gravity should provide some structural stability. But the outgassing rate of 180 kilograms per second is enormous. And if it continues to increase, as the comet reaches perihelion, the stresses on the nucleus could become critical. If 3I Atlas were to fragment during its hidden passage behind the Sun, we would not know until it re-emerged in December, and by then, the trajectory predictions would be even more uncertain. Instead of tracking one object, IAWN might have to track dozens of fragments, each following a slightly different path, each pushed by different non-gravitational forces. This scenario would turn an already challenging astrometry campaign into a logistical nightmare. The structural question leads to another: what is the size and shape of the nucleus itself? The estimate of 5.6 kilometers is based on the brightness of the object and assumptions about its reflectivity, or albedo. Cometary nuclei are typically very dark, reflecting only a few % of the sunlight that hits them because they are covered in a layer of carbonaceous dust and organic material left behind as the ice sublimates. But we do not have direct imaging of the nucleus of 3I Atlas, at least not at the resolution needed to see its shape. All we see is the bright coma, the cloud of gas and dust that surrounds and obscures the solid nucleus. To determine the true size and shape, we would need a spacecraft mission, a flyby, or orbiter, equipped with cameras and spectrometers that could observe the nucleus up close. For 3I Atlas, launched from another star system on a hyperbolic trajectory that gives us only months of warning, such a mission is currently impossible. We missed the opportunity with 1I Oumuamua, and we were only partially prepared for 2I Borisov. The dream of planetary scientists and astrobiologists is to one day detect an interstellar visitor early enough to launch a rapid response mission, an interceptor spacecraft that could reach the object, study it in detail, and perhaps even return samples to Earth. Such a mission would be the holy grail of comparative planetology, allowing us to directly analyze material from another star system without traveling light years to get it. Until that day, we are limited to remote sensing ground-based, space-based telescopes observing from millions of kilometers away, piecing together the story from photons alone. The mass estimate of 33 billion tons is derived from the size and an assumed density. Cometary nuclei are thought to have densities ranging from about 300 to 600 kilograms per cubic meter, roughly half the density of water ice because they are porous, filled with voids and cavities. If we assume 3I, Atlas is a sphere 5.6 kilometers in diameter, and use a density of 500 kilograms per cubic meter, the mass comes out to approximately 33 billion metric tons. This is a staggering number for perspective. It is roughly equivalent to the mass of 50,000 large ocean-going ships, or about 150 billion fully loaded semi-trucks. Yet in the context of the solar system, it is a speck. Jupiter's moon, Ganymede, the largest moon in the solar system, has a mass of 148 trillion kilograms. 3I. Atlas is a dust mote by comparison, but it is a dust mote moving at 210,000 kilometers per hour and carrying the chemical signature of an alien world. The velocity itself is a critical piece of the puzzle. 210,000 kilometers per hour, approximately 58 kilometers per second. This is far faster than the typical velocities of objects within the solar system. For comparison, Earth orbits the Sun at about 30 kilometers per second, and even the fastest comets, diving into the inner solar system from the Oort cloud, rarely exceed 50 kilometers per second relative to the Sun. The excess velocity of 3I Atlas is the hallmark of its interstellar origin. It arrived with a velocity inherited from its parent, star system, plus the motion of that star relative to the Sun. This velocity also determines the shape of its trajectory through the solar system, hyperbolic rather than elliptical, which means it is not gravitationally bound to the Sun and will escape back into interstellar space after its brief visit. The specific orbital parameters, the inclination, the argument of perihelion, the longitude of the ascending node, define the precise path of 3I Atlas through three-dimensional space. These parameters are determined by measuring the object's position in the sky over time and fitting a model orbit to the observations. For most objects, this is straightforward, but for 3I Atlas, the non-gravitational forces introduce uncertainty. The more the comet outgasses, the more its trajectory deviates from a purely gravitational path, and the more frequently astronomers must update their models. This is why IAWN officials stated that 3I Atlas is causing unique challenges for predicting its trajectory. It is not enough to calculate where the comet should be based on gravity alone. They must also model the rocket effect of the outgassing, and this requires detailed knowledge of the activity level, the direction of the jets, and the rotation state of the nucleus, all of which can change over time. The Comet Astrometry Campaign is designed to address this challenge by collecting dense time series observations over the TAN's two-month period from late November 2025 to late January 2026. Participating observatories will measure the position of 3I Atlas as frequently as possible, ideally every night, weather permitting. By comparing these measurements to the predicted positions based on the best available dynamical models, scientists can detect even small deviations and refine the non-gravitational force parameters. This iterative process of observation modeling, refinement, is how modern celestial mechanics operates. It is a conversation between theory and data, each informing the other, until the model converges on a solution that matches reality. The campaign also serves a secondary purpose. It is a training exercise for the global planetary defense network. The threat from near-Earth asteroids and comets is real, and while the probability of a catastrophic impact in any given year is low, the consequences would be so severe that preparedness is essential. IAWN and its partner organizations, including NASA's Planetary Defense Coordination Office and the European Space Agency's Space Situational Awareness Program, conduct regular exercises to test the IR, detection, tracking, and communication protocols. These exercises simulate the discovery of a potentially hazardous object and the subsequent efforts to determine its orbit, assess the risk, and, if necessary, plan a mitigation mission. Inclusion of 3I Atlas in this framework is unprecedented because it is not a near-Earth object, and it poses no impact threat to Earth. Yet its extreme activity and the resulting trajectory uncertainties make it an ideal test case for the kinds of challenges the planetary defense community might face with a real threat. If we can successfully track and model 3I Atlas, we demonstrate our capability to handle even the most difficult cases. And if we cannot, if non-gravitational forces prove too chaotic, or the object fragments into multiple pieces, then we learn valuable lessons about the limits of our current systems and where improvements are needed. This dual-nature scientific investigation and operational exercise gives the campaign a sense of urgency and importance that transcends pure curiosity. It is no longer just about studying an interesting comet. It is about protecting our planet and proving that humanity has the tools and the coordination to respond to cosmic threats. The emergence of 3I Atlas in early December will be a moment of collective focus. Telescopes around the world will turn toward the pre-dawn sky, searching for the faint, fuzzy glow of the returning visitor. The first detections will likely come from large professional observatories equipped with wide-field cameras and sensitive detectors capable of picking up faint objects against the brightening twilight sky. Once the position is confirmed and the recovery announcement is made, amateur astronomers and smaller observatories will join the effort, adding their observations to the growing database. Every data point matters. Every measurement contributes to the refinement of the orbit and the understanding of the non-gravitational forces. In the days and weeks following the reemergence, scientists will compare the observed position to the predicted position based on models that assume only gravitational forces. If the comet is where it should be within the expected margins of error, then the outgassing has not significantly altered its trajectory, and the mystery deepens. Why would such a violent, active comet not experience more substantial non-gravitational perturbations? But if the comet is not where it should be, if there is a measurable offset, then the detective work begins in earnest. Which direction is? The deviation is the comet ahead of or behind its predicted position along its orbit, suggesting acceleration or deceleration. Is it above or below the predicted plane, suggesting a perpendicular thrust? Each possibility corresponds to a different geometry of outgassing and a different physical model of what is happening on the surface of the nucleus. The true test will come over the course of the full 2-month campaign as the comet moves across the sky and the baseline of observations grows. By January 2026, scientists will have enough data to construct a detailed dynamical model that accounts for the non-gravitational forces, and they will be able to predict the your trajectory of 3I Atlas with much higher confidence. At that point, the object will be moving away from the Sun, heading back out into the cold depths of the outer solar system, and eventually beyond into interstellar space. It will fade from view as the distance increases and the outgassing slows, eventually becoming too faint to detect even with the largest telescopes. But the data will remain, the measurements, the spectra, the images archived and analyzed for years to come. Each one a piece of the puzzle that is 3I Atlas. And the question posed by Avi Loeb will remain as well, because the data can tell us what happened, but not necessarily why. The observation that the solar conjunction coincided with Perihelion, that the moment of maximum velocity and optimal maneuverability occurred during a period of total invisibility, is a fact written in orbital mechanics. But whether that fact is a coincidence or a consequence of design is a question that data alone may never fully answer. Unless, of course, the data reveals something unexpected, a companion object, a secondary trajectory, a signal that cannot be explained by natural processes alone. This is the edge where science meets speculation, and where the story of 3I Atlas takes on a dimension beyond the purely physical it becomes a question about the nature of intelligence and intention in the universe, and about our readiness to recognize the signs if they are there to be found. Part 2 of our story ends here, with the campaign about to begin, and the object still hidden, preparing to reveal itself. And in that revelation, perhaps to reveal something about the cosmos we thought we understood. We arrive now at the heart of the matter, the philosophical and existential questions that 3i Atlas carries with it through the darkness of space. What does it mean when we encounter an object from another star system, and what does it mean when that encounter is mediated by invisibility, uncertainty, and the tantalizing possibility of intentionality? These are not questions science can answer definitively, but they are questions science forces us to confront. The search for extraterrestrial intelligence has traditionally focused on radio signals, electromagnetic emissions that might carry information across the light years. Organizations like SETI, the Search for Extraterrestrial Intelligence, have spent decades scanning the skies, listening for patterns in the cosmic static that might indicate a deliberate transmission from another civilization. The assumption underlying this search is that intelligence announces itself, that a technological civilization capable of interstellar communication would want to be found and would broadcast its presence using methods we could recognize. But there is another possibility, one that has gained traction in recent years among scientists, like Avi Loeb and Jason Wright. What if intelligence does not broadcast, but instead sends physical artifacts, probes, spacecraft, or even simpler objects designed to travel between stars and gather information? This approach, sometimes called the zoo hypothesis or the berserker hypothesis, depending on the intentions attributed to the senders, suggests that the galaxy might be filled not with radio chatter, but with silent emissaries, traveling on trajectories carefully chosen to maximize their scientific return. The advantage of physical probes over radio signals is duration and information density. A radio signal travels at the speed of light, but it disperses and weakens with distance, requiring enormous power to be detectable across interstellar distances. A physical object, by contrast, can carry instruments, sensors, cameras, and possibly even samples. It can change course, perform maneuvers, and gather data over extended periods. It is in effect a message in a bottle, but one equipped with eyes and perhaps intelligence. If such probes exist, how would we recognize them? This is the central challenge addressed by Loeb and his colleagues in the Galileo Project, an initiative specifically designed to search for physical evidence of extraterrestrial technology in our solar system and beyond. The project uses a combination of telescopic observations, sensor networks, and data analysis to look for objects that exhibit anomalous behavior deviations from natural expectations that might indicate technological origin. The criteria are subtle, and the bar for evidence is high. Science does not allow for speculation without data, and extraordinary claims require extraordinary evidence. But the starting point is to look at objects like 1i Oumuamua and 3i Atlas, and ask the uncomfortable question, could these be something other than natural phenomena? For Oumuamua, the case rested largely on its unexplained acceleration and its unusual shape. Loeb proposed in a series of papers and in his book, Extraterrestrial, that Oumuamua might be a light sail, a thin reflective sheet pushed by radiation pressure, either from the sun or from a distant laser array. The hypothesis was controversial and remains so, but it is scientifically testable. If we ever detect another Oumuamua-like object, we can design observations to measure its reflectivity, its shape, and its response to sunlight in ways that would distinguish a light sail from a natural object. For 3I Atlas, the case is different. The object is clearly active, shedding gas and dust like a comet, and its behavior is largely consistent with natural outgassing driven by the sublimation of carbon dioxide. But the timing, the coincidence of solar conjunction with Perihelion introduces a new variable. If you were designing a mission to visit our solar system, and you wanted to perform a high-energy maneuver without being observed, you would choose this exact window. The Oberth effect maximizes the efficiency of any propulsive burn at perihelion, and the solar conjunction guarantees that no Earth-based telescope can track your actions. This does not prove intent, but it establishes motive. In the language of orbital mechanics, it is the optimal strategy, and the fact that nature has provided this opportunity at precisely the right moment is either a coincidence or a demonstration of planning. The speculation Loeb has offered about mini-probes being released from a mothership at perihelion is an extension of this logic. If 3I Atlas were not a comet but a carrier vehicle, or if it were a comet that had been repurposed or accompanied by technology, then perihelion would be the moment to deploy smaller craft. Each probe could be given a different velocity vector, sending it toward a different target: Mars, Earth, Venus, or even the outer planets. The parent object would continue on its hyperbolic trajectory, leaving the solar system while the probes remained behind, conducting long-term observations. This scenario is speculative, but it is not implausible. It is the kind of mission architecture that human engineers might design if we had the technology to send probes to another star system. And if we can imagine it, it is reasonable to assume that another civilization billions of years older might have implemented it. The key test will come in December, and the months that follow. If 3I Atlas reappears on a trajectory that matches gravitational predictions within the expected margins, then the natural explanation holds and the coincidence remains just that, a coincidence. But if there are deviations, if the non-gravitational forces are asymmetric in ways that cannot be explained by random outgassing, if there are secondary objects detected near the comet, then the investigation enters new territory. At that point, the data would demand deeper analysis, spectroscopic signatures that might reveal unusual chemistry or isotopic ratios, imaging that might show structures inconsistent with natural fragmentation, and long-term tracking to see if any objects remain inbound. Orbits around the Sun rather than escaping on hyperbolic paths. The IAWN Comet Astrometry Campaign will provide the positional data, but it will be up to the broader astronomical community to interpret what that data means. And this is where the scientific process shows its strength. Science does not begin with belief or assumption. It begins with observation, followed by hypothesis testing and peer review. If someone claims to have detected evidence of technology in the behavior of 3I Atlas, that claim will be scrutinized by thousands of experts around the world who will demand access to the raw data, the methods of analysis, and the statistical significance of any anomalies detected. This is how science separates signal from noise and truth from wishful thinking. But the process also requires openness to unexpected conclusions. The history of astronomy is filled with discoveries that defied expectations. Pulsars were initially thought to be signals from extraterrestrial civilizations before being identified as rotating neutron stars. Fast radio bursts were mysterious and unexplained until detailed observations revealed natural astrophysical sources. The same rigor that rules out false positives must also be willing to accept true positives if the evidence supports them. The broader context of interstellar objects and their role in the galaxy is another layer of This story, our solar system, is not isolated. It is part of a vast ecosystem of stars and planetary systems, all orbiting the center of the Milky Way galaxy. The Sun completes one orbit around the galactic center every 230 million years. And during that time, it passes through different regions of the galaxy, encountering different stellar densities and gravitational influences. Every star system sheds comets and asteroids through, gravitational interactions with planets and passing stars. These ejected objects become part of the interstellar medium, drifting through the space between stars on journeys that can last millions or billions of years. Some estimates suggest that there are trillions of rogue planets and interstellar comets wandering the galaxy vastly, outnumbering the stars themselves. Occasionally, one of these objects passes close enough to another star system to be captured or deflected. And very occasionally, one passes through our solar system where we have the chance to observe it. The detection rate for interstellar objects is expected to increase dramatically in the coming years as new surveys come online. Vera Rubin Observatory, currently under construction in Chile, will begin operations soon and will scan the entire visible sky every few nights, detecting millions of transient events, including asteroids, comets, and hopefully many more. Interstellar visitors. Each detection will add to our understanding of the population and diversity of objects in the galaxy, and each one carries the potential for surprise. We are living in the early days of interstellar astronomy, a field that did not exist until 2017, when Oumuamua was discovered. In less than a decade, we have gone from 0 confirmed interstellar objects to 3, and the pace is accelerating. Within our lifetimes, we may detect dozens or hundreds of such objects. And with each one, we will refine our models, our techniques, and our expectations. The question of whether any of these objects are technological rather than natural will persist and evolve. As our instruments improve and our datasets grow, we will be better equipped to answer it definitively. But until then, we exist in a state of informed uncertainty, guided by evidence, but aware of the limits of our knowledge. The role of organizations like IAWN in this new era cannot be overstated. Planetary defense is no longer a theoretical exercise. It is an operational imperative. The detection and tracking of near-Earth objects has improved dramatically over the past 2 decades, thanks to dedicated surveys like Pan-STARRS Atlas and Catalina Sky Survey. We now know the locations and orbits of more than 90% of near-Earth asteroids larger than 1 kilometer in diameter, the size threshold above which an impact would have global consequences. But smaller objects in the 100-meter to 500-meter range remain poorly cataloged, and these could still cause regional devastation if they were to strike a populated area. The challenge with interstellar objects is that they arrive with little warning. Unlike asteroids and comets born in our solar system, which follow predictable orbits, interstellar visitors come from random directions at high speeds. By the time we detect them, they are often already deep in the inner solar system, and we have only weeks or months to study them before they depart. This makes rapid response critical, both for scientific observation and for any potential defense scenario. The DART mission Double Asteroid Redirection Test, launched by NASA in 2021 and successfully impacted the asteroid Dimorphos in 2022, demonstrated that humanity has the capability to alter the trajectory of a small celestial body. This was a proof-of-concept mission, showing that kinetic impactors spacecraft deliberately crashed into an asteroid can change its orbit by a measurable amount. If we ever face a genuine impact, threat. This technique could be used to nudge the threatening object onto a safe trajectory, provided we have enough warning time. For an interstellar object moving at 58 kilometers per second like 3I Atlas, the dynamics would be different. The high velocity means that any deflection attempt would require significantly more energy, and the hyperbolic trajectory means the object is not bound to the sun, making long-term predictions more difficult. But principles remain the same: early detection, precise tracking, and the capability to intervene if necessary. The inclusion of 3I Atlas in the IAWN monitoring framework signals that the planetary defense community is thinking ahead, preparing for scenarios that may seem unlikely but are not impossible. The idea that an interstellar object could pose a threat to Earth either through direct impact or through some other mechanism is remote, but not zero, and the investment in tracking and understanding these objects is justified by the potential consequences too. The philosophical implications extend beyond defense and into the realm of identity and meaning. What does it mean to be human in a universe where we are not alone, or where we might not be alone? The question has been asked by every culture throughout history, and the answers have shaped religions, philosophies, and worldviews. For most of human history, the question was purely speculative, a matter of belief rather than evidence. But in the modern era, with telescopes that can see to the edge of the observable universe and instruments that can detect the chemical signatures of distant atmospheres, the question has become empirical. We are now capable of finding evidence of life beyond Earth. Whether microbial life in the subsurface oceans of Mars or Europa, or technological civilizations broadcasting from distant star systems, the discovery of such evidence would be the most profound event in human history. It would fundamentally alter our understanding of our place in the cosmos and our relationship to the vast web of life and intelligence that might exist throughout the galaxy. But the discovery might not come as a clear, unambiguous signal. It might come as a gradual accumulation of anomalies, objects that do not quite fit the natural model's trajectories that suggest optimization rather than randomness, isotopic ratios that hint at industrial processes rather than stellar nucleosynthesis. The challenge for scientists is to remain skeptical but open to pursue every anomaly with rigor, but without prejudice, to let the data lead rather than our hopes or fears. This is the tightrope that researchers like Avi Loeb, Jason Wright, and Darryl Seligman walk every day. They study objects like 3I Atlas with the same tools and methods used for any other comet, but they also ask the deeper questions, the ones that push at the boundaries of the known and the unknown. They are willing to consider hypotheses that others might dismiss as fringe, because they understand that E-Universe is under no obligation to conform to our expectations, and that the greatest discoveries often come from questioning assumptions. The story of 3I Atlas is still being written. The object is out there right now, hidden behind the sun, racing toward its perihelion at speeds that dwarf anything humanity has ever built. In a matter of days, it will complete that passage and begin its journey back out toward the stars. From our perspective, it will remain invisible for several more weeks until early December, when it emerges into the pre-dawn sky and the Comet Astrometry Campaign begins in earnest. What we find in those first observations will set the tone for everything that follows, if the comet is where we expect it to be, if its brightness and morphology match the predictions, if the trajectory is clean and the non-gravitational forces are within expected bounds, then 3I Atlas will take its place, alongside 2I Borisov, as a fascinating but ultimately explicable visitor from another star system. a cosmic postcard that tells us about the diversity and richness of planetary formation across the galaxy. But if something is different, if the comet has fragmented or brightened unexpectedly, if there are objects accompanying it, or if its trajectory shows signs of optimization, then the questions will multiply and the investigation will deepen. The data will be analyzed and reanalyzed, the models will, to be refined, and the global astronomical community will focus its collective attention on this single object, trying to determine what it is and what it might mean. In either case, the journey of 3I, loss through our solar system, represents a milestone in human exploration, not the exploration of space with rockets and astronauts, but the exploration of knowledge with telescopes and equations. It is a reminder that we live in a dynamic universe where the unexpected is always possible and where the boundaries of the known are constantly expanding. Every interstellar visitor is a gift, a piece of another world delivered to our doorstep, a chance to study material and chemistry and physics from a place we cannot yet reach. And everyone carries with it the tantalizing possibility that we are not alone, that somewhere in the vastness of space, another intelligence is also looking outward, asking the same questions we ask, and perhaps sending its own emissaries to explore the stars. As we wait for 3I Atlas to reappear, we are reminded of the patience required by astronomy, the willingness to wait for the universe to reveal its secrets on its own timeline. We cannot force the comet to emerge sooner. We cannot see through the glare of the sun. We can only prepare our instruments, refine our models, and wait for the moment when the geometry of orbits brings the object back into view. And when that moment comes, we will be ready. Telescopes across the globe will slew toward the designated coordinates, cameras will capture the first photons, spectrographs will split the light into its component wavelengths, and the data will flow into archives where scientists will begin the painstaking work of interpretation. This is the essence of science, the transformation of light into knowledge, the conversion of observations into understanding. It is a process that requires patience, precision, and humility, the recognition that the universe is far larger and more complex than any individual mind can comprehend, and that progress comes through collaboration and the accumulation of evidence over time. The story of 3I Atlas is a story about that process, about the way humanity collectively reaches out into the cosmos and tries to make sense of what we find. It is a story about the tools we build, the questions we ask, and the mysteries we encounter along the way. And it is a story that will continue long after this narrative ends, because the object itself will remain an entry in the catalogs, a data set in the archives, a reference point for future studies of interstellar objects and the nature of the galaxy we inhabit. In the end, the question posed by Avi Loeb, whether the timing of the solar conjunction and perihelion is coincidence or design, may never be answered with absolute certainty. Science deals in probabilities and evidence, not in absolutes. But the question itself is valuable because it forces us to think carefully about what we would expect from a natural object versus an artificial one, and to develop the tools and methods needed to distinguish between them. As we continue to detect more interstellar visitors, the sample size will grow, and patterns may emerge that help us answer these deeper questions. Perhaps we will find that all interstellar comets show similar activity and trajectories suggesting a common natural origin. Or perhaps we will find outliers, objects that defy explanation and demand closer scrutiny. Each discovery moves us one step closer to to understanding not just the mechanics of comets and asteroids, but the fundamental question of whether we are alone in the universe. For now, we wait and watch and prepare. The next few weeks will bring revelation one way or another, and the data we gather will inform not just our understanding of 3I Atlas, but our approach to every interstellar visitor that follows. This is the frontier of astronomy, the place where observation meets interpretation and where science confronts the unknown with rigor, curiosity, and a willingness to be surprised. And as the days count down to the re-emergence of 3I Atlas, we hold in our minds the image of that object hurtling through the darkness, a 5-6-kilometer nucleus of ice and rock wrapped in a glowing coma, trailing a plume of gas and dust, accelerating toward the moment of closest approach to the sun, hidden from our view, but not from the laws of physics that govern its motion. We cannot see it, but we can calculate its position, we can predict its trajectory, and we can prepare to observe it the moment it steps back into the light. That is the power of science, the ability to know what we cannot see, to understand what we cannot touch, and to reach across the vast distances of space with nothing more than light and mathematics and the collective intelligence of our species. 3I Atlas is a visitor from the stars, and in its journey through our solar system, it carries with it the echoes of another world, and the possibility, however remote, that we are witnessing not just a natural phenomenon, but a deliberate act of exploration by minds not our own. The answer to that question will come, not from speculation, but from data, and the data is coming soon. The countdown has begun, and the universe is about to reveal another of its secrets, whether we are ready for it or not. The human mind is not well equipped to process cosmic timescales. We measure our lives in decades, our civilizations in centuries, but the universe operates on scales of millions and billions of years. The journey of 3I Atlas began long before humanity existed, before our sun had planets, before the Milky Way had achieved its current spiral structure. The object we are tracking today is ancient, a fragment of a world that formed around another star in an era we can barely comprehend, and its arrival in our solar system, now in October 2025, is the culmination of a voyage that may have lasted tens of millions of years. Consider the forces required to eject an object from its parent star system. Comets, unstable. Orbits around their home stars can be perturbed by gravitational interactions with giant planets, or by close encounters with other stars passing through the outer regions of the system. These perturbations can increase the comet's velocity enough to overcome the gravitational binding energy of the star, sending it on an escape trajectory into interstellar space. Once free of its parent system, the object becomes a wanderer drifting through the near vacuum of interstellar space at velocities, typically between 20 and 50 kilometers per second, relative to the surrounding stars. The space between stars is not empty. It contains tenuous gas and thus the remnants of ancient supernovae and the raw material for future star formation. But the density is so low that an object like 3I Atlas would encounter almost no resistance, no friction to slow it down. It would coast through the darkness for eons, crossing light years at a daisy pace that seems fast by human standards, but is glacially slow on the scale of the galaxy. At 58 kilometers per second, 3I Atlas would take more than 20,000 years to travel a single light year, and the nearest stars to any given point in the galaxy are typically several light years apart. This means the object has likely been traveling for hundreds of thousands or millions of years, since it was ejected from its home system passing through the territory, as of countless other stars, most at distances too great to cause any significant gravitational deflection. But eventually, by chance, or by the subtle influence of the galaxy's gravitational field, the trajectory of 3I Atlas brought it close to our Sun. Close enough that the Sun's gravity began to dominate, and the object's path curved inward toward the inner solar system. This moment of capture, or rather, this moment of close approach, because 3I Atlas is not captured but merely deflected, marks the transition from interstellar traveler to solar system visitor. The velocity of 210,000 kilometers per hour is the result of two components: the object's intrinsic velocity through interstellar space, and the acceleration provided by the Sun's gravity as it falls inward by the time it reaches perihelion at 1.36 astronomical units. The gravitational acceleration will have increased its speed to the Proust maximum value, and this is the speed that determines the effectiveness of any maneuver performed at that point. The Oberth effect, named after the German physicist Hermann Oberth, is not a mysterious or exotic phenomenon. It is a straightforward consequence of the conservation of energy and momentum. When you change your velocity by a fixed amount, the change in your kinetic energy depends on your current speed, because kinetic energy is proportional to the square of velocity. A small change in velocity at high speed results in a large change in energy. This is why spacecraft performing interplanetary missions often execute their main engine burns at perihelion, where their orbital velocity is highest, thereby gaining the maximum benefit from each kilogram of propellant burned. For a natural comet, the Oberth effect still applies, but the thrust comes not from rocket engines, but from the asymmetric sublimation of ice. If the nucleus is rotating, and if the active regions are not uniformly distributed, then the outgassing will create a net force in a particular direction. This force acts like a tiny rocket engine continuously firing as long as the ice continues to sublimate, and its effect is amplified by the high velocity at perihelion. For 3I Atlas with its intense CO2-driven outgassing. This effect is substantial. The challenge for scientists is to model this effect accurately enough to predict where the comet will be weeks or months in the future. This requires knowledge of the rotation period, the location and intensity of active regions on the surface, the rate at which the activity changes as the comet approaches and recedes from the Sun, and the direction in which the jets are pointed. All of these parameters must be inferred from observations of the coma and tail because we cannot see the nucleus directly. The fact that IAWN has mobilized a global astrometry campaign specifically to track 3I Atlas tells us that the uncertainty is significant and that the stakes are high enough to warrant this level of coordination. This is not just an academic exercise. It is a demonstration of capability, proof that the international community can work together to track and characterize an object with complex, unpredictable behavior. The skills and techniques developed during this campaign will be dire CTY applicable to future scenarios involving potentially hazardous asteroids or comets, where precise trajectory prediction could mean the difference between a successful deflection mission and a catastrophic impact. But there is also the other interpretation, the one that refuses to go away. Despite the lack of direct evidence, the possibility that the timing of the solar conjunction is not a coincidence, but a feature. If 3I Atlas were designed or accompanied by something designed, then the choice of trajectory would be critical. A mission planner with knowledge of astronautics would recognize that perihelion is the optimal point for maneuvers and would also recognize that performing those maneuvers while hidden from observation, provides strategic advantage. In the context of exploration, this advantage might be informational rather than military, the ability to deploy instruments or probes without immediately revealing their presence, allowing them to gather data on the behavior and capabilities of any observers in the system before making contact. This is speculative, and it must be emphasized that there is currently no evidence to support this interpretation. The observed behavior of 3I Atlas is entirely consistent with a natural comet, albeit an unusually active one, and the coincidence of timing while striking is not impossible. Coincidences happen in astronomy all the time. Orbits align, eclipses occur. Transits and occultations provide brief opportunities for observation that are the result of geometry rather than intent. The question is not whether the coincidence exists, but whether it is statistically significant, whether the probability of such an alignment occurring by chance is so low that we must consider alternative explanations. This is where Bayesian reasoning comes into play. In Bayesian statistics, we start with a prior probability and initial estimate of how likely a hypothesis is based on our background knowledge, and then we update that probability based on new evidence. For the hypothesis that 3I Atlas is artificial or accompanied by artificial objects, the prior probability is extremely low because we have no confirmed examples of extraterrestrial technology, and the vast majority of objects we observe in space are natural. The evidence, the coincidence, of solar conjunction perihelion updates this probability, but not by much, because coincidences are common and the behavior of the object is explicable through natural processes. The posterior probability, the updated estimate after considering the evidence, remains very low. Not zero, but low enough that the natural explanation is strongly preferred. This is how science operates, not by ruling out possibilities entirely, but by assigning them probabilities based on evidence and updating those probabilities as new data arrives. If future observations of 3I Atlas or other interstellar objects reveal patterns that cannot be explained naturally, then the probabilities will shift, and hypotheses that are currently marginal may become mainstream. But until that happens, the default assumption is that we are observing natural phenomena, and the burden of proof rests on those who claim otherwise. The broader implications of interstellar objects extend beyond the question of artificial versus natural. These objects are samples of other planetary systems delivered to us without the need for interstellar travel. Every measurement we make of their composition, structure, and behavior adds to our understanding of how planetary systems form and evolve across the galaxy. The discovery that 3I Atlas is rich in CO2, for example, tells us that carbon dioxide ice can be a major component of comets in other systems, and that the conditions in the outer regions of those systems where comets form must be cold enough to allow CO2 to condense. This is consistent with our understanding protoplanetary disks, but it is valuable to have direct confirmation from a sample that originated elsewhere. The isotopic ratios of elements like carbon, oxygen, and nitrogen in the gas and dust of 3I Atlas will provide further clues. Isotopes are variants of an element with different numbers of neutrons, and their relative abundances are set by the nuclear processes in stars and by the chemical reactions in protoplanetary disks. Different stars and different regions of the galaxy may have different isotopic signatures, and by measuring these in interstellar objects, we can begin to map the chemical diversity of the galaxy and understand how it relates to the history of star formation and nucleosynthesis. This is astrochemistry on a galactic scale, using comets as messengers that carry information across distances we cannot yet traverse. The study of interstellar objects is still in its infancy. With only 3 confirmed detections, we are just beginning to glimpse the diversity that exists. But the future is bright. The Vera Rubin Observatory, when it begins operations, will survey the sky with unprecedented depth and cadence, detecting faint, fast-moving objects that would have been missed by earlier surveys. Estimates suggest that Rubin could detect dozens of interstellar objects per year, transforming the field from a curiosity into a major area of research. With larger sample sizes, we will be able to perform statistical analyses, looking for patterns in the orbits, compositions, and activity levels of these visitors. We will be able to compare them to comets and asteroids from our own solar system, identifying similarities and differences that reveal the underlying physics of planetary formation. Some interstellar objects may be compositionally similar to solar system bodies, suggesting that the processes of planet formation are universal. Others may be wildly different, revealing chemistries and structures that do not exist in our neighborhood. These discoveries will feed into models of planetary system formation and evolution, helping us understand not just our own origins, but the origins of planets around other stars. The connection to exoplanet science is direct. Over the past 3 decades, astronomers have discovered thousands of planets orbiting other stars using techniques like the transit method and radial velocity measurements. These discoveries have revealed a stunning diversity of planetary systems, with architectures very different from our own hot Jupiters, orbiting close to their stars, super-Earths that have no analog in our solar system, and tightly packed systems where multiple planets orbit within the distance of Mercury from the Sun. But exoplanet observations give us limited information. We can measure the mass and radius of a planet, and in some cases analyze the composition of its atmosphere, but we cannot directly sample its surface or its interior. Interstellar objects offer a complementary approach. They are fragments or representatives of other planetary systems, and by studying them in detail, we gain insights into the materials and processes that exist in those systems. If we can determine which star system a particular interstellar object came from by tracing its trajectory backward through the galaxy, we could even establish a direct link between the exoplanet observations and the physical sample. Currently, this is difficult because the trajectories are perturbed by the gravity of the stars they pass on their long journey, and because we do not know the exact motion of most stars millions of years ago. But future astrometric missions like Gaia and its successors will map the positions and velocities of billions of stars with high precision, giving us the data needed to perform these kinematic reconstructions. Imagine being able to say that 3I Atlas originated from a specific star system, one that we have studied with telescopes, and where we have detected planets orbiting. The comet becomes a direct sample from that system, a piece of physical evidence that we can analyze in laboratories here on Earth if we ever develop the capability to intercept and return samples from interstellar AR visitors. This is the dream of many planetary scientists and astrobiologists, the ability to study extraterrestrial material, not from meteorites that formed in our own solar system billions of years ago, but from active dynamic systems around other stars. The technology to intercept an interstellar object is challenging but not impossible. The key is early detection and rapid response. If we can detect an incoming object years before it reaches the inner solar system, we have time to design and launch a mission that could rendezvous with it. Study missions have been proposed for both Oumuamua and Borisov, but in both cases the objects were discovered too late for existing launch vehicles and spacecraft to catch up. However, with advanced propulsion systems like solar sails or nuclear electric propulsion, and with dedicated survey telescopes that can detect interstellar objects at greater distances, a rapid response mission becomes feasible. A mission could carry cameras, spectrometers, and sample return capsules, allowing us to bring back material from another star system for detailed analysis on Earth. The scientific return would be extraordinary. Every grain of dust, fragment of ice would be analyzed with the full suite of laboratory techniques: mass spectrometry, electron microscopy, isotopic analysis, revealing the composition and structure in far greater detail than any remote observation could provide. We would learn about the minerals, the organic molecules, the isotopic signatures, and potentially even about prebiotic chemistry or biosignatures if the object originated from a system with life. This is not science fiction. It is science planning. And multiple space agencies are actively considering mission concepts for interstellar object intercepts. The success of such missions depends on continued investment in survey telescopes, rapid communication networks, and advanced propulsion technologies. But the foundation is being laid, and it is likely that within the next few decades we will launch our first mission to an interstellar visitor. The story of 3. I-Atlas is a chapter in this larger narrative, a single object among billions that populate the galaxy, but one that arrived at a moment when humanity has the tools and the curiosity to study it in detail. The coincidence of solar conjunction and perihelion, the intense CO2 outgassing, the unprecedented inclusion in the IAWN monitoring list. All of these elements combine to make this object uniquely significant, not because it is necessarily artificial, but because it challenges us to think carefully about what we observe and how we interpret it. As the days count down to the reemergence in early December, the astronomical community is preparing the Comet Astrometry Campaign will begin on November 27 and will continue through the 27th of January 2026. During those 2 months, 3. I-Atlas will be one of the most closely watched objects in the sky. Every clear night at dozens of observatories around, the world telescopes will slew to its coordinates, and cameras will capture images that will be processed and analyzed within hours. The positions will be uploaded to central databases where orbital dynamicists will fit models to the data, refining the trajectory and searching for any deviations from purely gravitational motion. The results of this campaign will be published in scientific journals and presented at conferences, contributing to the growing body of knowledge about interstellar objects and setting the stage for future observations and missions. But beyond the science, beyond the data and the models and the journal articles, there is a human dimension to this story. We are a species that looks up to the sky and asks questions about our place in the universe. We are driven by curiosity, by the desire to explore and understand, and by the hope that somewhere out there we are not alone. The detection of interstellar objects is a reminder that the universe is vast and connected, that material and perhaps information flows between star systems on timescales far longer than human lifetimes. But inexorably nonetheless, every interstellar visitor is a thread in the cosmic web, linking us to places and times we can barely imagine. And every detection, every measurement, every analysis brings us one step closer to answering the fundamental question: are we alone, or is the galaxy filled with worlds and perhaps minds, engaged in the same search for understanding? The answer may not come in our lifetimes. It may come gradually through the accumulation of evidence from many sources. Interstellar objects, exoplanet atmospheres, radio signals, or physical artifacts. Or it may never come definitively, leaving us in a state of informed uncertainty, where the probabilities shift but never reach certainty. But the search itself is valuable because it expands our horizons, challenges our assumptions, and reminds us that we are part of something far larger than ourselves. As 3I Atlas completes its hidden passage around the Sun and begins its journey back into the darkness, we are left with the image that has defined this story: a 6-kilometer nucleus, wrapped in a glowing envelope of sublimating CO, 2 racing at 210,000 kilometers per hour through the optimal point for a high-energy maneuver, while completely hidden from the eyes of humanity. It is a moment suspended between observation and interpretation, between what we know and what we wonder. A moment that will be resolved in the coming weeks, when the veil is lifted and the data flows in. Until then, we wait. And in that waiting, we confront the limits of our knowledge and the vastness of what remains unknown. This is the essence of the scientific endeavor: the willingness to ask questions even when the answers are uncertain, the courage, follow the evidence wherever it leads, and the humility to admit that the universe is under no obligation to conform to our expectations or our desires. 3I Atlas is a visitor from the stars, and whether it is merely a comet or something more, it has already succeeded in doing what all great discoveries do. It has made us think more deeply, question more rigorously, and look more carefully at the cosmos we inhabit. The countdown to re-emergence continues, and the universe is about to speak. We will listen, and we will learn, and whatever we discover will become part of the ever-growing story of humanity's relationship with the infinite. Thank you for being with us. Please subscribe and leave a like.